Today we are going to discuss about the Ampere circuital law. In order to find out magnetic field induction due to a current carrying wire, already we discussed Biot-Savart law. That means using the Biot-Savart law, we can find out magnetic field induction due to a current carrying conductor. From this law also, it is called Ampere circuital law. From this law also, we can find out magnetic field induction due to a current carrying wire. When current passes through a wire, a magnetic field is produced. Say this is the wire, a magnetic field is produced around it. Okay? To find out magnetic field induction at any point, we may use this law also. So what is this law? The line integral of magnetic field induction around any closed path is equal to mu 0 times the current threading the surface enclosed by the closed path. So this is the current carrying wire, this is the loop. This is a loop. Okay, the line integral of magnetic field induction around any closed path or around any closed loop. So this is the closed loop. This is the closed loop. Is equal to mu 0 times current threading the surface. Surface means this is the surface. Current threading the surface enclosed by the closed loop. What is mu 0? Mu 0 is permittivity of the free space. Can you remember permittivity of free space? So B dot dl, the closed integration of B dot dl is equal to mu 0 I, where I is the current inside the closed loop. Okay? This law can be applied only for the steady current. When the current is varying normally this law is not used. Okay, this law is also called as analogous of Gauss's law in electrostatics. This law is also called as analogous or equivalent law of Gauss's law in electrostatics. Can you remember the Gauss's law in electrostatics? Total electric flux linked with a closed surface is equal to 1 by epsilon 0 times the total charge enclosed by the closed surface. Epsilon 0 was permittivity of free space. Okay? So what is the applications? So this is the current carrying wire. We have to find out magnetic field induction at this point. So this is the wire. I have to find out magnetic field at this point. So in order to apply this law, I require a closed loop. I take the closed loop like this. So this is the closed loop. That means in this figure, the wire is in the plane of paper and the Amperian loop is perpendicular to the plane of the paper. This loop is used to apply the Ampere's law. So therefore it is called Amperian loop. We may visualize the situation like this also. So this is now my wire is perpendicular to the plane of paper. So in that case what happens? Amperian loop will be the Amperian loop will be in the plane of paper. So here Amperian loop is in plane of paper and this is the current carrying wire. It is perpendicularly outward. The wire is like this. We know that for a current carrying wire, magnetic field is produced around it. So therefore, this is the direction of B here. This is the direction of DL. So what is the angle between B and DL? It is 0. If I take BDL here also angle between them 0. Therefore, what is B dot DL at the point P? B dot DL at the point P is BDL cos of 0 is equal to BDL. Therefore, around the entire Amperian loop, what is B dot DL? B dot DL is B integration of dl, b comes outside the integration. Why? Because at every point value of magnetic field is constant. Magnetic field is constant. Because I consider the Amperian loop as a circular one. Circle means equal distance from the center. At equal distance, value of b will be constant. Okay? So integration of dl means twice pi r, circumference of the Amperian loop. Okay? So what the law say? What the law say? Law say that b dot dl around the closed path C, b dot dl around the closed loop C is equal to mu 0 I. What is I? Current inside the loop. So this is the wire, this is the loop. So what is the current inside the loop? The current passing through the wire, it is I. So b dot dl means b into twice pi r. So what we get? So b is mu 0 I by twice pi r. That means magnetic field varies inversely to the distance of the experimental point from the current carrying wire. Magnetic field varies inversely. Magnetic field varies inversely with distance from the current carrying wire. Okay? But in this case, we cannot apply this condition. When R is 0, what happens to B? According to mathematics, when R is 0, B should be infinity. But we know that when a current passes through a wire, magnetic field is produced around it. We get the magnetic field maximum at this point. There is no magnetic field around the axis. Yes or no? We already discussed in the first class. Oersted experiment. If we place the magnetic needle here and here, when the current flows through it, there is no deflection of the needle. But when we place the needle here, the needle gets deflected. When we place the needle below and above the wire, the needle gets deflected. Okay? That means we cannot put this situation here. Because from experiment we know that when current flows through the wire, magnetic field is produced around it. So therefore, this law has certain limitations. This mathematical equation has limitations. We cannot apply that condition to when R is 0, what happens to B? When we know experimentally that when R is 0, magnetic field is 0. But this is for infinitely long wire. For finite length of the wire, what happens? In order to find out magnetic field induction for finite length of the wire, we cannot use the Ampere circuital law. We have to go for the Biot-Savart law. And using the Biot-Savart law, we are getting mu 0 I by 4 pi r sin theta 1 plus sin theta 2. Okay? Now, for infinitely long wire, what happens? Theta 1 and theta 2 becomes pi by 2. So, sin pi by 2, 1, sin pi by 2, 1, 1 plus 1, 2. So, these two get cancelled. So, what we get? So, we get mu 0 I by twice pi r. So, this value and this value are exactly same. Okay? That means we can find out magnetic field induction due to an infinitely long straight wire using the Ampere's law as well as using the Biot-Savart law. According to our syllabus, this is required. This is not required. This part is required only for the mathematical point of view. Or this law is required. This approach is required for entrance examination. There is another condition. If the magnetic field is at the one end of the wire, this is infinitely long, but this is at one end of the wire, then theta 1 is 0, theta 2 is pi by 2, sin 0, 0, sin pi by 2, 1. So B is mu 0 I by twice pi. That means if this is the infinitely long wire, magnetic field at this point, in the middle of the wire is mu 0 I by twice pi r, and magnetic field at the end is mu 0 I by 4 pi r. But sometimes another question comes, and they say that find the value of magnetic field induction at an internal point. If the wire is a thick wire. So in our case, in the previous case, we take a wire of negligible thickness. But in this case, they say that the wire is a thick wire having radius capital R. So here is the assumption. If we assume that the current is uniformly distributed throughout the cross section of this thick wire, so then we can find out magnetic field induction at an internal point. Normally we know that current always passes through the surface of the wire. But if we assume that the current is uniformly distributed throughout the cross section of the wire, then under that situation we can find out value of magnetic field induction at an internal point. If current is uniformly distributed, what is current per unit area? I by pi r square. R is the radius of the wire, and this is the Amperian loop. Okay, this is the point P. This distance is R. So what is B dot dl here? Here B dot dl is B dl. B dot dl is B dl cos of 0. So B dl. So around the entire Amperian loop, what is B dot dl? Exactly same, B into twice pi r as previous. What is the Ampere's law? Mu B, closed integration of B dot dl is equal to mu 0 times current threading the closed part. Current threading the closed part. Here, what is the current? Current inside this closed part. What is the area of this closed part? Pi small r square. Pi small r square. Therefore, current inside the closed part is current per unit area multiplied by area of the Amperian loop. What is the current threading the closed part? Current threading the closed part is current per unit area of the thick wire multiplied by area of the Amperian loop. And integration of B dot dl is B into twice pi r. R is the distance of the internal point. So in that case, we are getting this. 1 r get cancelled. This twice pi coming here. This is the mathematics you can find out. So under that situation, B directly proportional to smaller. That means if the wire is a thick wire, as we move away from the axis of the thick wire, value of magnetic field induction increases, and at the surface it becomes maximum. From where I make this conclusion? I make this conclusion from this equation. Mu 0 I by twice pi r square into small r. Capital R is the radius of the wire, it is constant. Other terms are constant. Only small r is varying. As I move away from the axis to the surface, small r increases, therefore value of magnetic field also increases. And at the surface what happens? Small r is equal to capital R. At the surface what happens? Small r is equal to capital R. Therefore, instead of small r I put capital R, 1 r get cancelled. It is mu 0 I by twice pi r. It is exactly equivalent to the previous value. Okay? Sometimes another question comes and they ask to find out, they ask to draw the variation of magnetic field with distance. From the axis of a thick wire carrying current. So under that situation what happens? From axis to the surface, magnetic field induction increases as the distance of internal point increases. At the surface, it becomes maximum, and at the external point, B varies 1 by R. From where this equation comes? It is similar to that of the previous case. Here only the wire thickness is negligible. Here we consider the thickness a large thickness. In order to find out magnetic field induction, at an external point of a thick wire, we may use the same approach as that of this. Because when we find out the magnetic field at an external point, we may neglect the thickness of the wire. We may neglect the thickness of the wire. So under that situation, the value of B varies like this. From axis to the surface, magnetic field increases as the distance increases. At the surface, it becomes maximum, and at external point B varies inversely with distance. Okay? And what is the value of B at the surface? What is the value of B at the surface? Mu 0 I by twice pi r. And what is the magnetic field induction? At an internal point, B is mu 0 I by twice pi r square into small r. This is entire terms constant, so therefore B proportional to small r. So at the axis of the wire, what happens? At the axis of the wire, what happens? At the axis of the wire, small r will be 0, So under that situation, if small r is 0, B is 0. Okay?